Recursion is the secret sauce to making many computer algorithms more simple than they first appeared. In this video, we'll use recursion to make a simple but effective Sudoku solving program. Hello everyone, my name is Mike and you're watching Polymath Unlimited. In this series, we are learning the C++ programming language by building our own Sudoku game. In the last episode, we fixed some issues with the program that were preventing us from moving forward. Now that this has been done, we are free to move forward and start adding more features to our game. In this episode, we are going to add a way for our program to solve a Sudoku board automatically. This might seem like a very complex task at first. After all, Sudoku is a fairly complex game, and some puzzles can be notoriously difficult to solve. However, it turns out there's actually a fairly simple approach that we can use here called recursion. Before we start writing our solver, let's briefly discuss what recursion is. In programming, recursion is when we have a function or subroutine in our program that calls itself. Probably the simplest example of this also happens to be my favorite way to break a program, having the main function call itself. Let's illustrate this by making a new program and simply calling main in the main function. If we try to run this program, we can see that it quickly generates a runtime error because it runs out of stack memory. This is because when the main function executes, it immediately calls main, which creates another instance of the main function that calls main, which creates another instance of the main function that calls main. You get the idea. The result is that our stack memory quickly fills up with function calls to main that never go anywhere because there's no way for the program to break out of the loop. This also illustrates how important it is to be careful with recursion in our programs, since it's pretty easy to make infinite loops like this that eat all of our memory without actually doing what we want. Let's look at a better example of recursion that actually does something more useful. We'll program a factorial function. This is a function that outputs the product of the input with all positive integers less than the input. So, for example, 5 factorial would output 5 times 4 times 3 times 2 times 1, or 120. Now, we could do this with some for loops, but there's actually a very elegant way to do this with a recursive algorithm. Notice that in our product, we have 5 times 4 times 3 times 2 times 1. But 4 times 3 times 2 times 1 is just 4 factorial. Same thing with 6 factorial, 7 factorial, and so on. In general, n factorial will be equal to n times n minus 1 factorial. So in our factorial function, we can simply return n times the factorial of n minus 1. In order to avoid the same infinite loop problem we saw in our recursive main function from earlier, we also need a base case. This is a condition that breaks out of the recursive loop. For our factorial function, the base case will be 0. So if we give 0 to our factorial function, then the function will return 1 since 0 factorial is defined to be 1. This breaks the recursive loop because this level doesn't call any further recursions. If we now make a simple I/O loop in main, we can prompt the user to give a number, and then the program will give the factorial of that number as output. This is all well and good, but what does it have to do with solving a Sudoku board? Well, it turns out that we can solve a Sudoku board by brute forcing using an algorithm called backtracking. This algorithm first chooses an empty square, then puts the lowest possible legal number on that square. Next, we do the same thing with the next empty square, and so on. Once we hit an empty square where any number we place is illegal, then we know we made a mistake somewhere down the line. In this case, we leave the square empty and set the previously modified square to the next legal value. If there are no more legal values for that square, then we just keep going back up the line of squares we have modified, increasing them to the next legal values. By repeating this algorithm enough, we are guaranteed to generate a valid solution for the board if one exists. Let's translate this algorithm into a recursive algorithm in C++. We'll create a bool function called solve and pass in a board state as an argument. The first thing we do is find an empty square. We can do this with some nested for loops and an if statement. If those for loops finish without finding any empty squares, then the board is already solved and we can return true. If we find an empty square, we'll loop through all the legal numbers for that square and try placing them on the board, then recursively call our solve function. If we placed the right value on that square, then the solve function will return true. So we can return true since a solution was found. Otherwise, we go on to the next legal number for that square and try again. If we have gone through all possible values for that square and didn't find a solution, then we backtrack by setting the square to 0 and returning false. The recursive iteration one level above the current solve iteration will then set the previously modified square to the next legal value and continue trying to find solutions from there. Now we can add a solve command to our game loop. In this command, we will simply call the solve function on our board. If we did everything right, then we should see the solution pop up on our screen. There's a subtle bug here, however. Suppose we have a board that we already have partially filled in, but we have a wrong value somewhere on the board. Since the solve function only modifies empty squares, it will never fix this wrong value, so a solution will never be found. While making this video, I actually also found a separate bug in our isLegal function that makes it so we can't reset grid squares to 0. I fixed this by explicitly making 0 always a legal value to place in a square. Anyways, back to our solve issue. We need a way to clear the grid before running the solve function to make sure we clear anything the player might have put in the wrong spot. Let's make a reset function that will reset a Sudoku board to its initial state. In the function, we'll loop through all the grid squares, and if any are greater than 0, then we'll just set them to 0. This works because in our code, we are interpreting negative values as initial values, so none of them will get cleared when this function runs. Now in our solve command, we can simply call the reset function before we call the solve function. If we then try that same case where we have a wrong value in the grid, we can see that our solve command still works. Just in case a solution is not found, we'll also output a message to the user letting them know there are no solutions if we didn't find one. Let's also add a feature that lets the user peek at the value of a single square on the board. This will be handy if the player wants just a simple nudge instead of looking at the whole solution. We'll add a hint command. The user will give us a square, and then we'll give the user the value of that square. To do this, we'll copy our board state into a temporary array, then run our reset and solve functions on that array like we did before. Then we'll output the value of the solved square so the user can see it. Now that we have a way to automatically solve Sudoku boards, we can build all sorts of new functionality into the game, including generating random Sudoku puzzles for the user to play. We'll learn how to do that next time. Until then, feel free to play around with this program and see what you might want to add to your own version of it. Make sure to share your ideas and progress in the comments. Thank you for watching, and I will see you next time.